Okay, so imagine this for a second. You're building a house.
Right.
You've done everything by the book. You poured the concrete foundation. You framed the walls. The wiring is, totally up to code. You are feeling good. But then you go to hang one single picture frame.
Uh-huh.
You tap the nail into the drywall, and the moment it breaks the surface, your kitchen suddenly transports 3 feet to the left, or the basement just, well, ceases to exist.
That is a terrifying image for any homeowner.
It's a total nightmare, but in the world of C and C++ programming, this isn't a nightmare, it's a Tuesday. We are talking about memory corruption.
We are. And that analogy is actually, it's perfect because memory corruption isn't just a bug. It's not like a typo or a button that doesn't click.
Yeah.
It is a fundamental instability in the universe of your program.
The laws of physics just stop applying.
They really do.
So today we're doing a deep dive into these invisible ghosts that haunt code. We've got a whole stack of technical notes here, official definitions from MIT, and some really hands-on guides on how to exercise them.
We're going to look at the what, the why, and maybe most importantly, the how do we actually fix this? And looking at the source material, I mean, for C and C++2, this is basically a survival guide.
Let's start with the what. We have the official definition here from MITRE. It's CWE 787. It sounds incredibly dry, out of bounds, right? But the implications are, well, kind of wild. What are we really dealing with?
So MITRE defines it as writing to memory outside the bounds of a buffer. But, and here's where it gets really interesting, it's not just about, say, copying too much data in a row.
Okay, hold on. We should probably unpack buffer for a second. I always just picture a bucket.
A bucket is a great way to think about it, yeah. In memory, a buffer is just a reserved space. Here is a bucket that can hold 10 integers. If you try to pour 12 integers into it,
You have a mess on the floor.
exactly, that's a buffer overflow.
Yeah.
It's the classic pouring a gallon of water into a pint glass. But the MITRE definition we're looking at is more nuanced. It points to corruption.
So it's not just spilling.
No. It can happen from incorrect pointer arithmetic,
Right.
which is just doing math on memory addresses, or from accessing invalid pointers.
Invalid pointers. That's like trying to deliver mail to a house that was demolished yesterday, right?
Precisely. Or trying to unlock a door that hasn't even been built yet.
Yeah.
If you access memory that wasn't initialized or memory that you've already released, you are essentially reaching into the void. And if you write something there, you might be overwriting a critical instruction for the CPU or, I don't know, a variable that controls your bank balance.
And that's why the kitchen shifts 3 feet to the left. The entire program becomes unstable because the foundation, the memory state, is just gone.
And the really scary part is it might not crash immediately. It could run fine for a week, silently corrupting data before it finally implodes. That makes detection so difficult.
That is the stuff of horror movies. So our mission for this deep dive is to figure out how programmers catch these invisible ghosts. Our notes break this down into two main philosophies: white box testing and black box testing.
I like to think of it as checking the blueprints versus taking it for a test drive.
That's good. I like that. Let's start with the blueprints. White box testing. The notes say this is the same as static analysis.
Right. So in white box testing, the key feature is access. You have the keys to the kingdom. You have the source code sitting right in front of you. You're not guessing what the program does. You are literally reading the instructions.
So the program isn't actually running.
No, and that's a crucial distinction. The program is at rest. It's a text file. You're effectively proofreading a novel before you send it to the printer.
Looking for plot holes.
Exactly. You're looking for logical inconsistencies. Hey, you opened this memory bucket here, but you never closed it down there. That's a memory leak. Or you're trying to put 100 items into a 10-item bucket.
But here's my question. Modern software has millions of lines of code. Reading that line by line sounds physically impossible.
Oh, it is. It's impossible for a human to do it perfectly. We get tired. We glaze over. That's why, while the concept is manual review, the source material really emphasizes that we use automated tools.
Tools that just scan the code for you.
Precisely. They parse the text of your code, the APIs you're using, and they look for known bad patterns. They know that if you use malloc to grab memory, you must use free to release it. If they see one without the other, bam, flagged.
So it's an inside-out approach. You're trying to predict failure based on the structure.
Correct. But predictions, as we know, aren't always reality. You can have a blueprint that looks perfect, but when you actually build the bridge and drive a truck over it, it collapses.
Which brings us to the test drive, black box testing.
Or dynamic analysis.
Yeah.
We shift gears completely here. In black box testing, we often don't even look at the code. We might not even have the code. We are testing the compiled binary, the executable itself.
We treat it like a sealed box. We just put inputs in and we watch what comes out.
Or we watch if the box catches on fire.
Right. And this is where the notes introduce fuzz testing. I have to say, fuzzing sounds kind of cute. It sounds soft. But reading this, it's anything but.
It is aggressive. Fuzz testing is basically interrogation. You use automated tools fuzzers to just bombard the program with inputs.
But not nice inputs.
Oh, no. Not polite inputs. We aren't typing in hello world. We are typing in 10,000 A's. We are typing in negative numbers where they shouldn't go.
Yeah.
Random, absolute gibberish.
You're actively trying to break it.
You're stress testing all the logic.
Yeah.
If I give this calculator a number that is longer than the universe is old, does it handle it gracefully, or does it try to write that number into a tiny memory slot and crash everything?
So white boxes, does this look right? And black boxes, does this act right?
That is the perfect way to put it. White box checks the form, black box checks the function.
Okay, so we've got the theory, blueprints, and test drives. But I want to get into the actual toolkit. The sources give us a deep dive on some specific tools, and they start with a real heavy hitter.
Valgrind. Valgrind is legendary in the C and C++ community. It's a framework for dynamic analysis. So we're back on the black box side for the most part, specifically the tool inside it called memcheck.
The notes make it sound like it's almost magic, but looking at the setup, it's not exactly plug and play. You can't just sprinkle Valgrind on your code.
No, there's definitely some friction there.
Yeah.
Valgrind essentially acts as a virtual machine. It inserts itself between your program and the operating system, and it watches every single instruction. But to do that well, it needs information.
The notes mention installing libc6, dbg.i386 packages. That just sounds like alphabet soup.
It does, but it's critical.
Yeah.
Those are debugging symbols for the standard libraries. Think about it. Your program relies on libraries to do basic things like print text.
Right.
If you don't have those debug symbols, Valgrind sees your program calling a library function, but it has no idea what that function is doing inside. It's like critiquing a movie when half the scenes are blurred out.
You need the symbols to see the full picture. And then there are the compilation flags. This part was fascinating because it shows how much gets lost between my code and what the computer runs. The source says you have to use the J flag.
This J is non-negotiable for this.
Yeah.
When you compile code, usually the computer strips out all the human stuff variable names, line numbers, it just wants machine code. JAG tells the compiler, hey, keep that metadata.
So if Valgrind finds a bug, it can say, you messed up on line 42 of main.cpp instead of just like error at memory address 0x00045F.
Exactly. It's the difference between knowing a crime happened and knowing which room it happened in. Without row G, you're just hunting in the dark.
But then we get to the optimization flags. This feels like a major trade-off. The notes recommend Actio 1. Why not Actio 0 for zero optimization? Wouldn't that be the most accurate?
It's a classic developer dilemma. Compilers are smart. If you use high optimization like Actio 3, the compiler might completely rewrite your code to make it faster. It might rearrange loops, inline functions.
So the code running on the chip looks nothing like the code I wrote on my screen.
Not at all. And if Valgrind finds an error in that highly optimized code, it might point to a line number that doesn't even exist anymore in your source file.
Chaos. So why not just go with zero optimization?
So Actio 0 gives you the rawest code, a direct translation. But the reality check in our notes warns about the slowdown. Valgrind is already slow. It's emulating a CPU. It can slow your program down by 20, maybe even 50 times.
Wow. So a 1-minute task takes an hour?
Potentially, yeah.
Yeah.
If you combine Valgrind's natural slowness with unoptimized code, you might be waiting all day. Dash 01 is the Goldilocks zone. It optimizes just enough to keep the speed reasonable, but it keeps the structure rigid enough that line numbers are still accurate.
It's about tolerating the slowdown to get the insight. You pay for knowledge with time.
Always.
Okay, so Valgrind is this powerful third-party tool, but what about the tools we already have? The sources mention using the compiler itself, GCC or G++A, as a defense mechanism.
This is your first line of defense. Before you even think about Valgrind, you should just be listening to your compiler. It's trying to help you.
We have a list of warning flags here. They feel like the dashboard lights in a car.
That is the best comparison. And what do most people do with dashboard lights?
And put a piece of tape over them and keep driving.
Exactly. And then the engine blows up. The compiler is warning you that something looks fishy.
So let's run through these lights. The first one is dash wall, which, logically, sounds like warning all.
You'd think so. But in compiler speak, dash wall is a lie. It actually just displays all the standard warnings. It's the baseline. It catches the obvious stuff like using a variable you never initialized.
So it's not enough on its own.
Not for the kind of deep dive we're doing. You have to escalate. That's where Dashvodantic comes in.
That sounds very strict.
It is incredibly strict. It forces your code to adhere to the official ISO standards. C and C++ have these strict rules, but compilers are often lenient. They let you get away with a little non-standard tricks. Dashvodantic is the teacher who demands you show your work exactly like the textbook says.
And Dashwextra.
That just enables newer warning messages that might not be in the standard wall set yet. It's like updating your virus definitions. Catches the newer, more obscure edge cases.
There is one more here that caught my eye because it sounds so dangerous. Dash conversion.
This one is crucial and, shockingly, often overlooked. It warns about implicit type conversions.
Implicit type conversion. Break that down for me.
Okay, imagine you have a variable that's designed to hold a massive number, say a long integer. It's a huge bucket. But then, somewhere in your code, you accidentally assign that value to a short integer, which is a tiny little bucket.
The data won't fit.
It won't. So the computer, trying to be helpful, just chops off the top part of the binary data to make it fit. It doesn't ask you, it just does it.
It decapitates my number.
It does. And suddenly your value of 4 billion becomes Ennicus 200. And here's the kicker. Your program doesn't crash. It just behaves wrongly. It calculates the wrong tax. It steers the rocket 2 degrees left. Dash while conversion screams at you the moment you try to shove a big number into a small hole.
That is such a subtle source of bugs. I can see why you'd want a warning for that. That could hide for years.
Absolutely. Those are the hardest bugs to find because the code runs successfully. It just produces garbage.
Okay, so we've covered the check engine lights. But now I want to talk about the heavy hitter in the sources. This feels like the SWAT team of memory detection. Address sanitizer. Or ASON.
ASON. Yeah, this really changed the game when Google introduced it back in 2012. Before ASON, you were mostly stuck with Valgrind, which, as we said, is slow. ASON is fast.
The mechanism here sounds like something out of science fiction. The notes use the term shadow memory.
It is a fascinating concept. So ASON is what's called compile time instrumentation. You activate it with the flag, fan sanitizer. When you compile, ASON literally injects extra code around every single memory access you make.
Okay, so it's modifying my code. What's it doing with this shadow memory?
It creates a parallel map of your application's memory. For every 8 bytes of your application's memory, ASON creates 1 byte of shadow memory. The shadow byte acts as a status tracker.
A tracker. Like a little security log.
Exactly. It tracks whether those 8 bytes are safe to touch. If the memory is good and allocated, the shadow byte says clean. But if you free that memory, or if it's outside the bounds of an array, ASAN marks that shadow byte as poisoned.
Poisoned?
That is the technical term. So every time your program tries to read or write to memory, ASAN does a super fast check on the shadow memory first. Is this area poisoned? If it is, boom. It stops the program instantly and prints a beautiful error report.
So it's like having a chaperone watching every single move the program makes, checking a list to see if you're allowed to be there.
That's a perfect analogy. And because it's so tightly integrated into the compiler, it's incredibly fast. It only slows things down by about 2x, which is nothing compared to Valgrind's 20x or more.
That is unbelievably powerful. But the sources mention some limitations. It's not a magic bullet for everyone.
No. The source notes we're looking at specifically highlight that this setup is primarily for Linux.
Right, that's a big caveat.
It is. ASAN relies on some clever tricks with how the operating system handles virtual memory mapping to create that shadow memory efficiently. While there are versions for other OSs now, the specific guide we're looking at is very Linux-centric.
And there's another requirement that links back to our whole discussion on testing types. ASAN is dynamic, right?
Yes. This is crucial to remember. Even though you set it up with a compiler flag, ASAN does absolutely nothing while the code is just sitting there. You must actually compile and run the program to catch the bugs.
So if I have a buffer overflow in a function, but my test never actually calls that function.
ASAN will never see it. It only watches the execution, not the text file.
Yeah.
It's like a speed camera. It can't give you a ticket if you keep the car parked in the garage.
That's a great way to put it. So we have Valgrind for deep, detailed inspection. We have compiler warnings for early detection. We have ASAN for fast runtime protection. I mean, we are armed to the teeth.
We are. But the notes end with a section called the reality check, which I think is the most important part of this whole conversation. Automated tools are not perfect. They catch a lot, probably more than a human eye ever could. But they don't catch everything. And even more importantly, detection is only half the battle.
Right. The source mentions a file, memoryleakfix.cpp. The implication is pretty clear. Finding the red flag is step 1. Step 2 is you actually have to go fix it.
You have to be the surgeon. The X-ray, which is your Valgrind or ISAN, can find the broken bone. It can show you exactly where the fracture is. But the X-ray cannot set the bone.
You have to understand why the leak is happening.
Exactly. Is it a bad loop? Is it an off-by-one error? A fundamental misunderstanding of a library? The tool can't explain the why, only the where. You still need to be a skilled engineer to rewrite the logic.
So what does this all mean for us? We started with this idea of memory corruption as a foundational instability, the basement just vanishing.
And we moved through the framework of detecting it. We've got the blueprints, the white box where we look at the structure. We've got the test drive, the black box where we fuzz the system and try to break it.
We looked at Valgrind, its need for debug symbols. We saw the power of the compiler itself and this idea of the shadow memory of address sanitizer.
It really highlights how complex this whole ecosystem is. It's an arms race between complexity and verification.
You know, looking at all of this, I'm really struck by that final concept, the shadow memory.
It sticks with you, doesn't it?
It really does. I mean, think about it. We are building software that is so complex, so prone to these invisible foundational errors, that we had to build other, even more sophisticated software just to watch it.
That's a mess problem.
It is. If tools like ASAN use shadow memory to watch our memory, it implies we've reached a point where manual coding has surpassed our own human capability to verify it. We can't trust ourselves anymore. We need software to watch our software.
It raises this massive question about the future of programming. If we need a machine to tell us if our code is safe, are we really in control of the code anymore? Or are we just guiding the tools that are?
That is something to think about the next time you see a segmentation fault pop up on your screen.
Indeed. It keeps us humble.
That wraps up our deep dive into detecting memory corruption. Thanks for listening, and keep your pointers valid.
Stay safe out there.